So actually, this is really a tutorial. The second half, I'll talk about stuff I'm actually doing, but this actually is very little of my work. So what I'm going to talk about is multi-hop attention, and the goal is to get you to to a transformer, which kind of is a very standard architecture that people use in natural language processing now. Raise your hand if you know what a transformer is. So okay, let's get a good sense. So raise your hand if you know what attention is in the context of neural networks. Okay, so a few people. Okay, so what about so if I say just neural network, do you raise your hand if you know like just plain feed-forward neural network? Okay, cool, great. Okay, that's actually so. I made a guess, and so I made a guess, and it was a good guess. I think the slides are roughly accurate in terms of pacing. Okay, good. So basically, we have really good neural architectures for some things. Like for images, we really know what to do. For some things, we don't. And what has happened is when we know underlying facts about the data that we want to study, we can do really well. And I guess in some sense, that's the theme of this workshop as a whole, in a kind of a larger thing. How do I encode structure about a problem that I have into a neural network architecture so that I can actually kind of save a lot of samples? And so classically meaning, say, 10 years ago, when you had a translation invariant thing that was on a grid, you use a COMNet. When you have a translation invariant thing, but also happens to have an order, then use an RNN. Recently, there have been kind of new things that we're going to talk about, but before any of those, there was straight feed-forward neural networks. And they're essentially not good at anything. Nevertheless, we're going to say what they are. So a fully connected feed-forward network eats a vector and outputs a vector. It is a composition of functions of the form f1 up to fk. Each f is a linear and then some sort of pointwise nonlinearity. So you take a vector, you linearly transform it, and then you do something to each coordinate independently. And that's kind of a classical feed-forward network. So you optimize each of the linear transformations in such a way that you fit your training data as well as possible. And great, it doesn't work that great. I mean, nowadays there are situations where fully connected feed-forward networks are better than linear transformations. That's about the best you can say right now. Really, they don't work very well for things because there's no structure in them. You can actually fit them to things. It's just usually you can do something better. Okay, so what's something that actually works? Well, COMNets work. COMNets are the same as fully connected networks, except all the linears are convolutions. So you specialize. You say, well, I'm not going to just take any linear. I'm going to take convolution. And the first thing that this means, if you have a n by m image that you're inputting, well, a straight up fully connected network would have to have nm times however many parameters, whereas a COMNet just has the filter size. So convolutional networks are just fully connected networks, except all the linears are convolutions. By the way, just is a weird thing here because there's also something interesting that happens because a convolutional network has the property that it's kind of invariant to the input size in a sense, or not invariant, it's equivariant with respect to the input. So a fully connected feed-forward network, if you give it a vector of size d, you have to, well, it's not if you give it, you have to give it a vector of a certain size. And that's all it takes. A COMNet, you can scale the input size. It doesn't care. It'll just make more outputs. Okay, so sequential networks, which we'll talk more about because they're useful for thinking about what we're going to talk about later. Inputs come in as a sequence. So this is, we know we have an ordering in addition to kind of the normal. So it's not just z, it's z with an order. So we have, for example, an input sequence and output sequence, and the output sequence is some function of everybody up to where you are now. So let's ignore this one. Well, not this. Let's not. So kind of classically, the first few times people saw this kind of data, what they did was they just have a fixed memory size, and each location is a thing, and you just essentially have a fully connected network going over that. Again, that doesn't work that well. What you can do a lot of times better is recurrence, and that is the idea that whatever transformation you do at a certain time step, it's the same. It doesn't matter. So that lets you have kind of a, you can tail out as long as you want in your memory. So the most kind of basic recurrent neural network, you have an input sequence, x0 up to xm, and output, well, the input sequence can go on forever. You have an output sequence, and you have something called you have the hidden state sequence. So these hidden state sequences correspond to in the layers in the middle of the feed-forward network we talked about before. Except the difference is now these are just going to go on forever. So instead of having a finite number of hidden outputs, you have an infinite number. The reason you can do this is you just push this forward after every step. So for each x, for each location, you have your current input and the kind of next, the current hidden state and the next input, and that allows you to output the next hidden state, and then your output is some function of the hidden state. And the recurrence means that you're doing the same thing at each time step. Now this isn't Markovian because you keep the hidden state. So it's not just f of xi. It's really not Markovian, but it does mean you do kind of the same transformation at every step. I mean, modulo the fact that you're keeping some hidden transformation around. OK, so great. Those kind of work OK. There's all sorts of problems optimizing these things. Like the classical proponents of recurrent neural networks said, oh, they're really great because you can cover a sequence and remember everything about the sequence. But of course, if you look at it for 2 seconds, you'll recognize that, if you really did remember everything about your sequence, some tiny wiggle over here is going to blow up to some gigantic thing over here, and it's not really possible. And really, every recurrent neural network that works has a very quickly, the transformation really quickly forgets information. It has to, because otherwise, you would have some sort of dependence on initial conditions, and you couldn't actually train the thing. OK, so that's kind of where things were. I'm going to now go, but before people started talking about attention, I'm going to make an aside because it's kind of important. We've been talking about these, I have some xi, whatever, but often in language, at least, the inputs to a neural network are words or indices. They're not things that you can, like you think about neural networks doing something with backprop. You have some weights that you can push a gradient through. If I give you indices, I can't push a gradient through those things, and well, that's kind of a problem. So you need to do something. The standard thing that people do is embeddings. So the simplest thing, actually, OK, it's written on here. So the standard thing people do to get vectors from indices or vectors from discrete objects, if you only have a finite number of discrete objects, you just associate a vector to each discrete object. It's kind of weird because I came from applied math, and this is like so obvious it's hard to, it's like, well, of course, because that's just like the rows of a matrix or something like that, right? But this was kind of a surprisingly big deal in neural network world. But yeah, it's, OK, so now, from now on, I'm going to kind of, when I talk about words, I'm going to kind of conflate the vector that's associated with that word, or if I talk about an index, I'm going to conflate the vector that's associated with that index and the index. But there is actually a name for this process of taking an index and getting a vector out of it. It's called an embedding. And of course, you can think of that as multiplying a weight matrix against a sparse matrix, or you can think of just that as extracting a row from a matrix or something like that. OK, so let's go back to the recurrent language model or recurrent network. So one thing that people kind of use neural networks for, recurrent neural networks for, is for language models. And language models means you take some corpus of text. You have an input sequence, which is all the words in the corpus. And you try to, given all of these words, predict that one. This is what a language model is. So I give you word 0 up to word n-1, and your job is to predict word n. And you do this by grabbing some gigantic corpus of text, and you predict. So when you are doing this, again, how do I get words into, how do I get vectors out of these? Because this recurrent network is using vectors. Well, I have a lookup table. And so once you've done, once you've done your processing, you have your y hat. What's a y hat? Well, if I want to, so this is maybe something, and the something usually ends with a softmax. And a softmax means the size of this yi is going to be the size of my vocabulary. So for each one of these words, this word came from a set of, say, k possible words. So I have an embedding matrix of size k to get the input. And I have k possible outputs in the same way. And usually, I would put a softmax here to say, oh, what's my output probability? So softmax is does everybody know what softmax is? OK, great. So I want to get a probability distribution over the output, so I put a softmax, and great. So this is a language model. And if you think about training a language model, what you're training is kind of a, well, so it looks like this. So you input something, you encode it, you update with the hidden state, and you have your decoder embedding. This was the G, and there you go. Now, if you're generating text from this thing, what do? You take your input, you encode it, go to the state, you go to the decoding. And now, if I want to get text out of this, if I actually want to use this to generate text instead of just as a model of probabilities of things, I have to sample. And it's not necessarily the correct thing to do. There's other things that are more sophisticated, but the simplest thing to do is just sample that output distribution. You get something, and now I plug this back in to the encoder embedding, get the state, get the decoder, sample, take that sample, plug it back in, and go on. And so this is how, if you give me a seed, I can generate new stuff. Right? So the reason I'm making this picture here and talking about recurrent networks a lot is because I think it can be helpful when you think about multi-hop attention. Multi-hop attention can be thought of as this thing turned on its side. So basically, an RNN is a non-Markovian random walk. Right? So how does an RNN work? So these dots all correspond to words. Right? And you start at some word, and you update your thing, you get a probability distribution over words that you might end up at. Then you have this probability distribution, I sample from it, I get some word. Now, I can't draw the thing, because I have my history there too. The history isn't drawn here. So this is a non-Markovian random walk, because I'm keeping the hidden state along as well, right? Yeah? Is it? OK. So I add that sample into the thing, and I update my hidden state, I get a probability distribution out, I sample from it, and so on and so forth. And that's how an RNN works. OK, so now we're going to kind of change gears slightly. So what we talked about is COMNets and fully connected nets and RNNs. Those went from just plain vectors as input to grids of various sorts as inputs to grids with order. And then now there's this thing, which is what if you have a set? So a lot of people are going to talk about graph NNs here. So I won't talk that much about it. But actually, it does happen a lot of times that your input is a set, and you really want to deal with a set of things, right? And a set really has some clear structures. First of all, it's permutation invariant. Second, you can, if you want to do a graph, you can have edges. So only certain things in the set, certain coordinates in the set talk to other coordinates of the set. But just the simple, what do I do if my input to my neural network isn't a sequence or a grid or anything like that, and it doesn't have fixed locations. It's literally a set. Well, attention is kind of the current correct solution to that problem. So first, we'll talk about an easier solution to the problem, which is a bag. So if someone gives you a set and you want to get a vector out of it, well, the simplest thing to do is to average the things in the set. And again, I'm doing this terrible thing where a set means set of vectors, and I assumed you did something to get whatever it was that was your original inputs into vectors. It could be a lookup table. It could be something else. So I'm going to keep making this mistake. So it says bag of vectors. People say bag of words, and that means a union of words. But here, we mean a sum of things. So the simplest thing you can do if someone gives you a set and you want to get a vector from the set is just average it. So you can be slightly more clever if your V's kind of are arranged nicely, if the way you've featurized your various things kind of keep some information. This actually may not be that destructive. So we all know that we can recover from sparse things. So actually, a lot of times you can recover this set from the sum. You know, it's not necessarily so destructive. You can be clever about the way you take averages. You don't have to take averages just all one big average, whatever. But honestly, just taking the average of a bunch of vectors is surprisingly useful. If you want to do something fast without thinking about it, just a lot of times just take bags of things, and it's really, really good. A lot of neural net people consider this as if bags of X works on your task is bad. I'm not sure if that's true. There are lots of good tasks that bags work really well for. I already said this. OK, so there are some tasks where bags work really well. Recommender systems is a classic example. I mean, if you're Facebook and you want to classify you want to kind of decide what a user wants to see or something like that, then you could have an index for every single user and have a vector just for that user. But actually, it can work quite well to just take an average of all the things that that person has looked at or something like that. You don't need any more structure, and it's fine. So there are lots of places where just taking a bag works. Another classic example is Word2Vec. Just taking bags of Word2Vec vectors is, well, I guess they call it fast text now. So taking bags of fast text vectors is a really good solution. If you have like 100 labeled data points of something, let's say you have a sentiment analysis task and you don't have that much labeled data. Taking 100 labeled examples and using a bag is actually just an essentially instantaneous baseline that works really well a lot of times. It's really good for retrieval as well. It doesn't work for a lot of things. Bags obviously don't work in vision. Convolutional nets, in some sense, were the thing that came after bags of SIF features. Doesn't work well at translation in particular. So bags are like the simplest thing you could possibly imagine doing. Someone gives you a set, I want to get a vector out of the set. Bags are a really simple way of doing it. Let's see where we. OK. So now we're going to go to the next level of difficulty. So somehow bags are really simple and easy and effective, but they fail at a lot of things. And so we'll get to the next level of difficulty, and the next level of sophistication. Next level of sophistication for sets is attention. And again, there's this whole other path of graph NNs that I'm not going to talk about because I think Xavier is giving a whole lecture on just graph NNs tomorrow. So in some sense, attention you could think of as a sequential processing of a set. Multi-hop attention is a sequential processing of a set. And a graph NN is like a parallel stream approach, although that'll be broken down at the very end when I talk about a transformer. OK, so attention is a probability distribution over your inputs. That's it. And that depends on some computational state and inputs. And when people talk about hard attention means that you have just one thing active. So your weighting is 1 in one place and 0 everywhere. Soft attention means you have some kind of continuous probability distribution. So in machine learning, there's been a long history of using attention for various things. So, I mean, you have to have, people always say, oh, humans use attention. OK, great. I don't know anything about humans. But but in computer vision, there is a really long history of kind of trying to use something that looks like saccades. Say, well, I don't want to take my whole image. I just want to look at one location, then another location, then another location, and integrate that information. So a lot of these early things, here, kind of here. Yeah, here too. These are all hard attention. So they were methods of, like, I'm going to look somewhere in an image, and then based on what I see in the image, I'm going to kind of decide where I should look next, and where I should look next, and where I should look next. And a lot of times this was kind of, previously this was inspired by kind of human vision. At some point it started to be like, well, we don't have the kind of computational firepower to eat the whole image at once. Modern vision systems do not do this because you just throw things through a GPU, and it seems better to just classify everything everywhere. We have the computation to do it, and might as well. We can discuss that more actually later. So all these papers were hard attention. So usually this is kind of attention over location and say, where should I look at next? I think the kind of more important predecessor or kind of precursor to the modern notion of attention neural networks is in language processing, and particularly in translation. So the kind of modern attention for neural networks came from translation. And so the idea here is that you talk about an alignment. And what's an alignment? And sorry, this is super blurry. So I don't read German. I think this is German here. So it says, and they actually illuminate your way through the rest of the book. And then there's some German translation, which I don't know German, and it's too blurry for me to read, so I'm sorry. But the idea is that English and German are close enough as languages that for each word here, you can decide what, and these aren't actually words, these are roots, these are graphemes, right? So each grapheme here can kind of be mapped to some grapheme over here. Now, classically, like in these original texts, they talked about hard attention again. Each word gets mapped to some other word, right? Later on, people said, okay, well, maybe you want some distribution. So for this word, actually, if you look at this column, this is the distribution over words that it aligns to, right? So before, we seemed to be talking about attention. I said a probability distribution over some inputs given some state. Here, the state is where you are. So for example, at the word actually, the probability distribution over inputs here would be the inputs, so to speak. And at the actually, you have this distribution here, right? So again, what's the notion of attention in this setting? What's the definition? It's pretty general. It's a distribution over inputs given some current state. Okay? So in the beginning, the initial versions of attention and translation were hard attention. It was what's called an alignment. Later on, they did soft alignment. So when you think about this distribution over words in the source, it wasn't used exactly the same in vision, right? What they did was they said, okay, let's optimize. Let's take my current output sequence and a kind of, my current input sequence and a possible output sequence, and I will run an optimization, say what's the best alignment of those two things. And the NLP people said, okay, well, I don't want to do a combinatorial optimization, so let me make soft attention so I can push a gradient through, so I can kind of optimize a soft alignment. In vision, the thing we were talking about is somehow the notion of focusing on a location. So in NLP, I would say the first paper, or the kind of, and surprisingly late, the kind of in the translation literature, the first paper that explicitly talked, as far as I know, about attention or soft alignment as attention in the sense of focusing is Dmitry Badnew, 2014. And this paper, I think, basically, this is the paper that showed that attention is a thing. It was a translation paper. Basically, they got the state of the art in neural translation, and they used single hop attention. So we'll talk about what multi-hop versus single hop attention is in a moment. But this really improved state of the art in attention, state of the art in machine translation. And up until that point, what people were doing, they were using pure recurrent networks. So state of the art, slightly before this paper in neural machine translation, was you take an RNN, you eat the input sequence, you get a vector, and then that means you had to encode the entire information content of that input sequence into one vector. Then you take that vector and then you run an RNN to get an output, right? And so this means that all the information of the input has to be encoded in that vector. What attention did, and notice there's this notion of soft alignment that's explicitly here. What the attention does is it means you don't have to store the entire sentence in the vector that you're going to decode from. It means that that just gives you some context, and then when it's time to decode, you just decide which words you're mapping to. And it makes a huge difference. Like attention on the encoder is the kind of keystone of modern neural machine translation. So now if we talk about attention, so that was kind of, that paper was kind of in this vision or in this kind of recurrent network in the sequence setting. What about with bags? What about attention over sets? Well, that just means a dynamically weighted bag. So what did we say a bag was before? A bag is just, I give you a set and I output the sum over the vectors in the set. Instead of just taking the sum, I take a weighted sum. This is what attention means in the context of sets. I don't want to take my set and process it as a sum. I want to weight the sum. Now, how should I weight the sum? Again, we're talking about attention in this setting of neural networks, so the weights depend on the state of the machine and the inputs. So the standard approach is softmax attention. I'm not going to talk about hard attention so much more. So softmax attention is literally you just take softmax. So you might have some current state. So H, I didn't write what, oh, I did, I said hidden variables. OK, so that should be state, hidden state variables. So I just take the inner product of my current hidden state variables and hit them against the set, and I take a softmax of that. So that gives me a distribution over these things, and I can sum them. And so this is kind of a dynamic reweighting of the sum depending on my current hidden state.
So is there also another approach which allows these coefficients Ci to vanish?
I
mean part of the coefficients to vanish.
Like to be exactly zero? Yeah. I mean, you can do things like that, but honestly, like you don't want to do that at train time usually. I mean, so there's reasons why you might want to do that at test time, right? There's reasons why you might not want to look at a bunch, like everything.
Okay. The reason why I'm asking is that allowing the coefficients, the weights to vanish, effectively means to dynamically rebuild the bags.
Yes.
I mean, that's also another dimension of attention, right?
So I think it's the same thing. I don't think it matters. I think that interpretation is exactly the same whether or not something is zero or not. It's just the dynamically, like something can be partially in the set. That's all. So I don't even think that's a stretch. I think that's the correct way to think about what's happening. You're saying, well, I think this is in the set this amount. And the zero is just a computational thing. Like sometimes it's useful computationally if something is exactly zero.
Okay.
But yeah, I mean, really, you should think of this as exactly as you're thinking of it. Like, I don't want the whole set. I want some subset of it. OK, well, subset. It's just, it's partially in the set. OK, and again, like there are reasons why you might want to actually have something zero exactly for computational reasons. But usually, if you're training a thing with backprop, you don't want anything to be exactly zero because it's bad. But of course, there's exceptions to that as well. OK, so this is soft attention over bag. And this is, again, everything we've been talking about is what's called single hop attention, in the sense that I have some inputs, I have some kind of state, and I make attention, I get the thing, and I make an output. And that's great. So the kind of cool thing about attention with bags is it's essentially a generic computational mechanism. That should scare you, because every time your method is generic, it doesn't mean it's optimal for your problem. Right? That's kind of this basic rule of the universe. Somebody says, oh yeah, this works on everything. No, it doesn't work on your problem, right? So attention is a completely generic computational mechanism. So that's kind of good and kind of scary. but yeah, it really is. The point is, let's ignore these two for a second. The reason why it's been so important and the reason why it's been so successful is this last bullet. So you can't just ignore structure, and you can't say, well, I have a generic thing, it'll work on everything. No, you have to keep structure, and you have to use the structure of your problem. The cool thing about attention as a mechanism for building function approximators is that allows you to inject the domain knowledge or inject the structure when the neural network is running at test time or at train time, not when I'm architecting the neural network. So what does that mean? So, well, I'll show you some examples in a minute. It has other nice properties that are really good. So it deals very cleanly with sparse inputs because a sparse input you can just think of as a weighted bag. These are kind of, this part of the slides are reasonably old. I think this is true, but people don't care as much as more. So again, we talked about in this RNN thing that you run over the RNN and somehow information has to keep, like, this is not, so everything here is these and these all are about sets or grids or whatever. This is a specific, this bullet is specific to sequential RNNs used for kind of text things. And the idea is that back in the day when people were using RNNs, all the information had to be held in the vector, which is the current hidden state. And so it's very hard to keep information because, again, you have this dynamical system thing that if the information is kept all the way back, a small change here blows up over here. So attention actually fixes that because, you know, at a given time, you can look back as far as you want, and you just decide based on the attention weights whether you're going to push information through. OK, so using attention as a set mechanism seems surprisingly, like, it's, again, surprisingly new. So again, we talked about this paper in the context of translation. This is kind of attached, again, to RNNs for handwriting generation. So these two were different kinds of attention. So here in this paper, the weights, the CI, depended on where the thing was in history. Again, it was a sequential input, and the location told you what weight to use. For translation, it was content-based. In other words, the hidden state of the RNN at a given, over a given word told you what the weight of that word was. And then kind of for more general problems, these are all kind of sequence. These are both sequence problems, kind of more generally. Oh, let's eat sets with these things. There's Jason Weston et al. The memory networks paper, and then the neural Turing machine and pointer networks. And these are kind of, it's kind of surprisingly late. I'm sure I'm just don't know something because this is a very natural idea. OK, so now I'm going to talk a bit about memory networks. So everything I talked about now is attention, just the idea of, oh, I make a weighted average. And everything up until about 2014, for example, the Banu paper and the machine translation papers, and in fact, in other NLP tasks, they'd done what's called single hop attention. In other words, you had some input somewhere, you looked over the outputs, you made a weighted bag to get your final thing before you make an output, and then off you go. So what the idea in memory networks and DNC, differential neural computers, is let's actually do attention. We'll update our kind of hidden state, and then with that new hidden state, we'll do attention over the inputs again. We'll update the hidden state, and we'll repeat and repeat and repeat. And so this allows kind of very interesting computation. Let's see, what time is it? 2:40. OK, so this allows you to. I should really have a. So the thing that they use in this paper is what's called the baby tasks, and you have things, little stories like Joe went to the kitchen. Joe picked up milk. Joe went to the bathroom. So you have these little stories like, oh, Joe went to the kitchen, Joe picked up some milk, Joe went to the bathroom, Joe put down the milk, Joe went to the bedroom, where's the milk? So this actually isn't that bad, and RNN probably could do this. But what's important here is what you have to do if you're a stupid machine reading this question is stupid machines work by matching words. So first you say, oh, you're asking about milk. OK, well, I see milk here. But it doesn't say where, put it down. Oh, but Joe, it also asked about Joe. I mean, I see milk here, but this sentence also, oh, Joe is in this sentence with the milk. So now I'm going to look for Joe. Oh, here's Joe here. And now, well, if I just look at the last mention of Joe before the milk, it's here, so it's the bathroom, yay. And that's the answer I can return. So the point is there's this notion of kind of looking at this, saying, oh, what's associated with that? Joe's associated with that. Where is Joe? Joe is here, here, here. But I want the last one before the milk, and that's here, and I should output bathroom. And you're laughing. That is literally what the neural network does, which is, in some sense, boring, but in some sense, incredible. Like,
as a parent, this is a problem I have to solve every day.
OK, where's the milk? So you can actually, so multi-hop attention is explicitly designed to do things like this. So let's see what multi-hop attention looks like. So the original, like Jason's original paper didn't have, in Jason's original paper, you couldn't push a gradient through the whole thing. There was some tricks about training it without actually doing gradient descent. Sina actually made it so you can push a gradient through the whole thing. It's actually technically, at the point, people didn't believe it, that it was possible, but he did it anyway. Now it's super normal. OK, so again, we talked about attention. So this is one step of attention. So you have a current hidden state of the kind of process. You look over your input vectors, and again, this is a set of inputs. Here, we can think of this as a set of memories. Here this is, say, M naught, M1 equals this, M2 equals that, M equals this. So these are your M's. So you have your current hidden state. You look at your set of things in memory, and that's why they call it a memory network, even though it's all about attention. I think it's a very bad name. It should be called an attention network, but whatever. So you attend over these. You take the softmax, and then with that softmax, you take the weighted sum of the things, and then that goes back into this, and you do the next step, right? So we already wrote this down as a formula before. This formula is I wrote CIs instead of PIs, which is annoying. Sorry. These are C's. So this is one step. Again, this is one step of attention. Do we want to go? Let's draw the picture first. So now I showed one little thing. You take this hidden state, you go, you do some attention, you make an output. That updates your hidden state. You attend over the inputs again based on this as your query vector. And you read and you output and so on and so forth. And when you think about what that's doing, it actually does this. You can trace what the thing is attending to, and it really does do, oh, milk, milk, Joe, bathroom, whatever. So let's write that in actual, let's actually write something, not a picture. So you fix it, so how does a memory network work, or how does multi-hop attention work? You fix a number of hops, you initialize your hidden state to be whatever it is, and I did it again. That was a U in the previous slide, and now it's an H again, sorry. So this H was that U. So you have some input set of memories that you're going to attend over, or objects that you're going to attend over. So what you do is you find attention weights here, and holy crap, these are C before, P in the previous slide, and now they're A. Sorry. So these are the attention weights. Again, you just take your current hidden state and multiply it against all the properties, and you get this dynamic weighting of the input set. You output some of those. You output the sum of those with those weights. You get a new hidden state. and you repeat. And then once you've done enough hops, you output that hidden state, and then that can go to something else to answer a question or something like that. More realistically, and let's talk about this for this particular thing, we have to talk about how we turn things into inputs, how we turn things into outputs, and so on and so forth. And I can't remember whether, yeah. Okay, so you have to kind of think about some way where you're going to get you're going to featureize your m's, and you have some way that you can featureize. So there's two places you need to featureize your m's. You need to featureize your m where you're computing the input attention, and then there's some way you need to featureize your m's when you're computing the sum on the output side, right? And so once you have those featurization rules, then you can do exactly the same as before. The featurization rules are really important. And so a few slides ago, I said, oh, it's a completely generic computational mechanism. That's really great. So the cost is you have to decide what this is going to be, and that's actually important. But it's important in a good way. It means that you can design this thing so that on the fly it's behaving properly. So in particular, for a task like this, the way you might featureize this object, so here the input is the set M1, M0, M1, M2. You could actually have just all the words, but that's probably really crappy. So a simple way to featureize this would just be a bag over each of these sentences. And that would fail completely because you need to know when these things happened. So for example, a simple way of featurizing these would be a bag of words over each of these, but then you have a special word saying what time it was. So let's reorder these, because it's always better to go backwards from this. So M1, M3, and 4. So you might have this is equal to this plus the word time 4 plus time 3 plus time 2 plus time 1 plus time 0. So you might have a special word for each of the times, and I might have some other special words, whatever. But that featurization is important. That's the way you make this thing work, right? You have to put information about the problem into that featurization, otherwise it is completely generic. So for that particular example, it needs to know the time, and if you don't give it that time, it's dead. Okay, let's ignore this. What time is it? Okay, I want to talk about transformers, so let's go fast. So let me say this one thing, because we're supposed to be talking about geometry. You can definitely put that information in the way you featurize things, right? And this, you have a lot of power here. The way you decide how you're going to arrange your features makes a really big difference. In particular, you can add any sort of geometric information you want. Okay, let's quickly look at this picture one more time just to get some other idea of what a memory network is doing, and then we'll get to transformers. So if you remember a sequential RNN looks like this. You input something, and this is how we generate, say we did a language model with a recurrent network. You eat some word, you encode it, that gives you a state, you decode it, and you sample, that gives you a new word. And this is what you're doing at test time, not at train time, right? This is how you're sampling a new sentence from a seed. So I sample something, I shove that back into the encoder, and I repeat, right? A memory network is this on its side. You don't sample, and you're not moving through. You're not moving. So these aren't these xt plus 1, xt plus 2. They're not words that you're walking through. It's not you're walking through words, but you're walking through attention hops. So again, let's pretend that each of the hops in my memory network were designed to have the same structure. They don't have to. They don't have to be recurrent, but they could. If they did, then I would eat my input. It would get into some state. I would get my output thing that I sum. I do a softmax over it, and instead of sampling, notice the sampling is missing here, I take that whole sum and I push it back in. And then I go through my state, I output some memory, and then I do some. So what you can think about it, instead of like the way an element RNN works or something like that, is it eats something, it immediately makes a decision, outputs that, and then that's its output, and it takes the next step. What this does is it kind of thinks about all the possibilities, says what would that weighted sum of possibilities look like, makes a change to what it might want to do, tries that a couple more times, and then after a couple of steps of this, then it makes an output. And if you kind of think about it as that random walk we saw before, what we did was we start at some location, we have some probability distribution, and we sample. Here, the things on the right is kind of what's in its head, so to speak. Like, you start with some point that gives you a distribution over possible things to sum up. You use that distribution, you turn it back in, that gets fed in and transforms into a different distribution, and you repeat that process a couple times, and then you get an output that you can sample from. Okay, so that's a memory network. Now, memory networks were kind of like, they kind of worked, but on a few toy tasks, but they never really worked. So the transformer is kind of like the evolution of this, and it's the modern version, and it really, really works. The difference in NLP from 2017 to now is the difference in vision from when AlexNet came out. There's been a huge change. I mean, it's really hard to overstate the change in NLP in the past 2 years because of transformers. So transformer is fundamentally, if you're going to do a thing with text now, just use a transformer. You don't even think about it. Just grab it and do it. It's by far the best thing. The nice thing is, as memory nets and as attention more generally, it is a completely general architecture. It eats sets. So what is a transformer? It is the same thing we talked about here. It's multi-hop attention, but it has three kind of changes, three important changes. They're listed in decreasing importance. Residual procs is not that important. It's just an effect of the other two. Multi-head attention is important, but it's not that important. The kind of critical thing that makes this work is multi-hidden state propagation. So let's see what that means. So if we looked at a memory network from before, you started with some set of inputs, you fix a number of hops, you get attention weights, which are the softmax of your hidden state against all the things in your set. You update the hidden state, and you sum the things that were embedded, and that gives you your new hidden state, and then you repeat. So this is what we're going to call single hidden state, because you have one hidden state that's propagated through and updated. Well, I mean, in this case, we're saying it's an RNN because everything changes, right? So if you, under very specific things, and again, this was the thing we were talking about before, right? There are, a diffusion on a graph fits this if you kind of make the correct everything, and that'll kind of go to some fixed distribution. But in general, I'm allowed to have all sorts of transformations on this in between. I've just made a very simple thing. And so there's nothing forcing this to be in any way going to any sort of fixed point or in any way converging as a function of hops. Also, you only take a finite number of steps usually. OK, but so this is single hop attention. It's multi-hop attention, but with a single hidden state propagation. The really key feature of a transformer is you have multi-hidden state propagation. You're not just propagating one hidden state through the network, but rather you have a hidden state for every single memory or every single input. You don't have to have it for every single input, but the idea is that you have multiple H's. Just for simplicity, we'll write one for every single input. So again, what you do is you take the hidden state associated to each input, and you compute the attention weights for that particular input's hidden state. You update that particular input's hidden state with the attention over everything, and then you repeat. But you do that for all the hidden states in parallel, right? So look at the difference between the two updates. In one, you had just one H that you propagated through. There was one vector. Here, you kind of have multiple threads. So before I talked about multi-hop attention as kind of sequential processing versus like graph as parallel processing. This blurs the two because you are in parallel running all the attention threads. But each attention thread, each attention hop thing, if you kind of trace it through, it's kind of working sequentially, but it's not. But they all run in parallel. So again, the difference between the transformer and what we had before was in that line. So you have multiple hidden states that you're propagating simultaneously. This makes a huge difference. One of the main important things this allows, in the previous thing, there was no reason to attend over the hidden state, really, because it interacts with all the things in the set. What happens here is each hidden state is interacting with all the other hidden states when it's updated. So this is a much more powerful mechanism, because before, what was happening is basically you could think of as the set of inputs, the m's being fixed. And this touches the m's and then updates itself, touches the m's and updates itself, touches the m's and updates itself. This guy gets to do something more powerful. It has a hidden state over every single m, so you can touch all of those, and then you update all of those, so all of them can change. You're not touching the initial m's at every step. Yes?
So the hidden states are generated one by one, right?
It depends. That's an implementation detail. The answer is no, because you're doing it on a GPU, and they're supposed to be done in parallel. So it's not like you update one of these, then you update all the h's and repeat. That's not how it's coded anywhere.
Based on the graph you showed before, it's like I have a hidden state 1 and update 2.
Right. So for the single hidden state thing, you do that. But here, you update all these together. So I can't.
What do you mean by all other hidden states?
Because at the next layer. So the point is, maybe if I draw. So before, you had something like this. You have H. H comes in and talks to all these guys, gets a weight. So we have a vector over these guys. H talks to all of them, gets some distribution over these, and then sums them up, and that outputs the next H, right? Yeah. What this guy is doing is you have an H over every single one of these. Right? And you have some query vectors start with, whatever, it doesn't matter how you start the process. But each one of these talks to all of them, gets a distribution for itself, and that, if you think about this one just before, it takes a distribution of these, gets this, and then you update to right? So each of these attends over all of them, transforms itself, and puts itself here. This guy does the same thing here. So everybody does that at the same time. It's not like you do this one, update it, and then you do this one and update it, or anything like that. Again, this is, I don't want to be too categorical, because there is at least one implementation that does this for various reasons. But most of the time, you take this guy and you hit it against everybody. At the same time, you take this one, hitting it against everybody, and then you update everybody together. Yes?
So are you keeping the number of hidden states constant throughout the network, necessarily?
OK, so what people do on, like the standard transformer paper has, or the 2017 transformer paper has one of these for one of these. However, the way machine learning literature works right now is you can change any one thing and make a paper. So I promise you, if you decide I want to have like 4 of these instead of 1, or whatever change you think of, there is a paper probably doing that. What I would suggest is, if there's a good reason for you to do that, just do it. And what? OK. So that was one thing. We talked about, that's probably the most important thing. OK, so if you get one moral from this whole talk, it's like use transformers for your set and natural language processing needs. The next important thing is multi-head attention. That's complicated. I have 2 minutes. So let's just say that you run, instead of doing this once, you have several of these running in parallel this way, and you mix them up after each step. It's important, but it's not that important. Then the final thing that makes this thing work is, because you're making all these changes, you really have to allow these guys to just reappear here, because you don't want to churn them up too much every step on purpose, especially in the beginning of training. So you all the weights, all the transformations that get you from here to here have residual connections to allow you to just copy this to here. But yeah, that's it. So that's what a transformer is, and that's how it fits in the history of attention. And really, it's kind of crushing NLP. I don't know, how many of you saw the OpenAI, the GPT-2 thing? Okay, so look this up because it's amazing. So OpenAI said, okay, we have this really great language model that we're not going to release because we're not actually open, and it's going to destroy the world. And it is a really good language model. It does things, you give it little prompts and it generates stories, and the stories are amazing from the prompts. What's really funny is they said, okay, we're not going to release this thing because it's so good, anybody could use it for terrible things. Within 3 days, someone at Facebook had just built the same thing because it's all done on PyTorch, whatever. The point is, it is really good. They were not lying how good it is. It is also not going to destroy the world because or if it was, then it will because anybody can redo it. But the point is, look up the GPT-2 and see how good language model has gotten, and the end.
Awesome. So let's thank Arthur. And we'll be back in 20 minutes.